electronic sockets, but we need it in our design. Next week, or maybe at the end of this lecture, we will discuss also the inverter cell. Okay. So now, DC to DC converter. Why we need this converter? Why we need to convert the DC to DC? See here, this is DC to DC converter. DC to DC converter. Portal DC chopper. And this load. Input positive, negative, this V load, this I load. And here, solar cell panel. Sometimes I need to rise the voltage generated from the solar cell. This is D, and this is V load. Sometimes I need to rise the voltage generated from the solar cell to reach to the load with higher than the generated voltage from the solar cell. Maybe this load, the load need 100 volts. The load need 100 volts, DC 100. But we have solar cell generate 50 volts only. So connected to DC converter to set up to step up the voltage. Okay, step up voltage from 50 to 100.
Just a step up.
This first circuit. Second circuit, maybe I have load need 50 volts and the generated voltage 100. So I can convert 100 volt to 50 by using steps down converter or step down DC to DC converter. Buck converter. Okay? Step up and step down.
So,
Same idea of the transformer, but the transformer is AC to AC converter, AC voltage to AC voltage, but here, no, DC to DC, DC to DC. So the input DC, input DC, DC input, DC output, and temperature and light, the input of the solar cell, temperature, DC to DC converter, DC input, DC output, okay, DC input to DC output, solar cell, DC input to DC output, but I don't know which one I needed. Also, if we use step down DC converter, step down voltage means step up current. We down the voltage means rise the current, or if we rise the voltage, down the current. Right. We will check it now. So we have, there are 13 or 14 types of DC chuck wiring, but we need just step down, step up. That's it. So DC to DC converter. Either step down or book converter. Or step up, boost converter. This is in general, but there are a lot of types of DC to DC converter, but we will focus on these on. Okay, and step down, we will focus with load of R or load R plus L. Resistor only or resistor with inductor. And step up with R only. Any question, please?
So, the resistance is constant there?
R, resistance, yes.
Yeah, that's it's constant, and it post up, step up.
Step up, post converter, just resistor. Okay, post converter. So, our class, we will focus on R and R plus L resistor and resistor plus inductor for step down or buck converter. For step up or boost converter, we will focus on the load only pure resistor, no inductor. Why no inductor? We will explain later why does resistor no inductor. So here R and R. This, we need just these circuits, okay, in general. But sometimes, why we convert the DC to DC? Okay, to make the voltage lower or upper than the generated voltage, but the load is just R and R plus L. No, sometimes we need to connect DC motor. We need to speed control of DC motor. We need this circuit. Okay, you need this. Okay. You need this one? No? No. In general, this DC to DC converter switch, and this is VG, and this V out, V out, VD input voltage to the converter, out output voltage from the converter, and this is switch S switch on off switch. Last week we said power electronics devices, thyristor, inverter, thyristor, transistor, field effect, transistor, MOSFET, used as a switch on off. So the switch here is any control device as thyristor or transistor, BJT, MOSFET, FETs, any control device, not diode, no, thyristor or control means by trigger will be on or no trigger off. So this switch is thyristor or transistor, MOSFET, any switching device, controlled switching device. Okay? Now, we say DC to DC converter, convert the DC to to DC, continuous to discontinuous. What it mean by continuous and discontinuous? See here. We input with time DC voltage. DC voltage, so the magnitude here V. While V output depend on the switch. You have two cases. This VD, V out, VD, V out. You have two cases. If the switch on means this is got up, it's short circuit. The switch S on means V out equal to VD. V out equal VD. V out equal to VD. Why? Because short circuit. Short circuit. This voltage same this voltage same this. This point same, this same. So now, this VD. V out equal to VD. Now, when the switch is off, when the switch off means this is open circuit. It's open circuit. Open circuit, V out will be 0. Open circuit, no voltage, no current. Reach to the load. No voltage, no current. So V out will be 0. 0. This 0. Then, again, the switch will be on. On. Then off. On. Off. Depend on the frequency. On, off, depend on the frequency of the switch. Depend on the frequency of the switch. On, off, on, off. See, this is continuous. This does continuous. Or this does continuous.
Continuous.
This does continuous. On, off, does continuous. This is continuous.
Without on and off.
All time
On.
B on. Okay, so this is continuous. This does continuous.
That one goes to continuous one.
To infinity. Depend on the battery. On to infinity. Okay. So continuous does continuous. Any question about this concept? Why we say continuous to does continuous? The DC to DC converter convert the continuous signal to does continuous. But I don't know if this voltage as a DC more than this or less than this voltage. This is input, V input, and this is output. But we don't know if V out more than V in or less than. Depend on what? Depend on the circuit. If the circuit is step down, so V out less than V in. If the circuit step up, so V in less than V out. I will repeat this concept again. This next page. You need this one. Take your time to write it. You need it or okay? Okay, so now again. Input voltage V input VD, we say this continuous and output voltage V out on off on off. This output voltage does continuous. Does continuous. Here. This time is T on. And this time T off, and this time TS. This is on time. On time means the transistor or the switch, thyristor, any device use this. On. T off, when the device, thyristor, MOSFET, field effect, transistor, BJT off, so this is time for off. TS is one period and includes the on time and off time. Includes on time and off time. So now T on when the switch device has thyristor or BJT on. On. T off. Off time. When the switch device has thyristor or BJT or field effect is off. BJT, MOSFET, any device. You can just switch on off. That's I don't need any calculation for amplifier terms as AV, voltage gain, or current gain, or power gain. No, we need just the switch as on off. That's it. So no perfection for on off terms. No perfection.
So-
Just on off switch. Open circuit, short circuit. So yes.
The two, this is page 3. Two, the diagram on 2 and 3, what's the difference?
This one. This one.
Yes, what's the difference between the one you draw here and for the continuous and the discontinuous?
Same.
That's what I'm saying. The other one, 2, is it the same?
The same.
Same.
On, off.
Just add T on, T off, TS. Same. Continuous. That's continuous. I repeated that.
Okay, you just repeated it there. Okay, just to have that TS. The,
Yes, just add
Okay,
TS,
just to have
T on,
TS.
T off. Yeah.
I was just wondering why we have the same thing.
Any question about this one? Okay. This TS will repeat it for n times. Maybe this signal repeated 20,000 or 10,000 or 5,000, 1,000. Depend on the frequency of on or of the switch on off. Repeated 20,000 or 1,000, depending on the frequency. So TS switching time. Switching time maybe in second or millisecond, microsecond, depending on the design. Where TS equal 1 over Fs. Fs is the switching frequency or chopping frequency or sampling frequency. Sampling frequency. But, sampling this term is using for communication topics. For power electronics, he used just switching the frequency or chopping the frequency. Okay? have on off. We have on off, on off, on off, on off. It define the duty cycle. The duty cycle of the DC to DC converter is the on time to total time. Is the ratio, maybe percent or maybe value per unit, on time to total time. So the duty cycle, D equal T on divided by TS, or T on, because TS 1 over F, 1 over Fs, or duty cycle equal Fs times T on, or maybe duty cycle also T on, because Ts is T on plus, see here, Ts equal T on plus T off. So T on plus T off, where Ts equal T on plus T off. So duty cycle is the percent ratio or per unit ratio between T on to Ts. On time or on period to all period for one period. Okay, why? Because on off repeated, and maybe 1,000 or 2,000 depending on the frequency. So you will take just one period because it's similar, should be similar period, on off, on off, on off, on off. Okay. On time maybe equal to off time, or less than off time, or more than. T on maybe more than T off, maybe equal T off, or less than T off, depending on the design and data given. Any question, please? Any question? No? Now, we say DC to DC converter divided to two types, step down and step up. Two types, okay. But maybe there is another type, is a step down, step up converter. Step down, step up converter. But in our class, we just step down and step up converter. Step down and step up converter. We need just these types. Okay. There are 13 or 14 circuits. Step down, step up, step down, step up, first quarter, second, fourth quarter circuit. Okay, yes.
What's R and L? Is R resistance?
See, we will study step down converter using R resistor,
Okay.
the load, R load, and R plus L inductor.
Okay.
Okay, and step up just R resistor.
Okay.
Okay,
Okay. Thank you.
so RL means R plus L resistor plus inductor.
Okay.
Now, we'll start with step down converter. Step down or up converter. Step down or up converter with system load. With system VD plus minus collector, emitter, base. This current ID and the current. This ID is control circuit. Why here control circuit? To control the on and off the transistor. This is BJT transistor. BJT. Okay. And here R load. This is V load. VL. And this is IL. Bipolar junction transistor. You can replace this transistor by field effect, or by thyristor, or by MOSFET. Okay? Or EGBIT. Now, most practical circuit implemented using EGBIT, insulated gate bipolar junction transistor. Why EGBIT? Because EGBIT used for high level voltage, for 11 kilovolt or more. So they use EGBIT, IGBT, insulated gate bipolar junction transistor. And why it's used for high voltage? Because the base terminal is isolated, so it can carry high current, high voltage, very high current, high voltage, because the base is isolated with the base is infinite resistor at the base terminal. So it's called insulated, similar to MOSFET. But the problem in MOSFET, the MOSFET is high cost. The material of the MOSFET is high cost, so the insulated gate polarization is low cost. But this circuit this is BJT, bipolar junction transistor, and you can remove this one and replace it by thyristors. And any switching device, any control switching device. This one. Oh, now operating mode. We have two operating modes. On state, off state. On state, when the switch R VD, when the switch is on, short circuit. Okay, so here V out equal to VD. V out equal to VD. And off state, when the switch is open circuit. This is switch. This is switch. Switch is mean thyristor or transistor or any power electronics device. And this is V out. Here V out equal to VD, and here V out equal to 0. V out equal to VD and V out equal to 0.
Thank you.
Any questions, please? No? Okay. Any question? No? Now, let me explain why this converter called step down or converter. Now, see, V input, V, pure DC, V. V output, the thyristor or transistor or switch on, so V out equal to VD. This T on. And if the switch is off, I mean this open, the output to zero. Then this T off. It's the same. This one, same. Okay. Same figure. Okay. On, off. But we need just one period. This is period is TS. Now, for resistive load, the current in resistive load and phase voltage or same voltage but different amplitude. So I out I out this I out, but here VT over R and 0, then VD over R, then 0. Okay, so on off. When the thyristor or switch off, the current should be 0. Okay, open circuit. We need just V out average and I out average or DC. V out average and I out average or DC. But sometimes we need RMS also. Why to measure the efficiency. Okay, so we will discuss V out, I out as a DC and RMS, and you will know why this called step down. Just to draw the figures. Second period, this one. TS also.
So
And this is T on again. This is T off again. Okay, I repeat it and
how
times.
do you add it in the equation?
No, as just one should be take just one period to analyze signal. Just one period. Okay. Okay, just this one. Okay. Yes.
What tells it it's on and off again? What turns it on and off?
On and off.
Yeah.
Time.
Yeah. Like what determines it's on and off?
Depend on the switch. Maybe the switch will be on for 0.5 millisecond and off for 10 millisecond.
Oh, okay.
Depend on the switch, on off. But what the term decide this time on or this time off period, okay?
Yeah.
This term or this circuit will decide on off. This one. using MATLAB. Next time I will explain it. MATLAB control this on-off time. Okay, using MATLAB you can just double click on the transistor and you can enter the on time and off time. Okay, but practically no, it's circuit.
Yeah.
Include circuit, capacitor, resistor connected together to generate pulse. Okay, to generate pulses maybe. Okay, or pure IV. Okay, to get on.
Okay.
And the time of on off depend on the value of the capacitor and resistor. Okay, because the charge and discharge discharge voltage and current. Okay,
Okay.
and period for each charge and discharge.
Okay.
Charge and discharge concept discussed in next lecture in inverter.
Okay.
So now, why we call this is step down or buck converter? This one. See, if we calculate VDC. VDC is the DC output voltage or average or mean. Okay? Average or mean voltage. VDC equal 1 over TS, 1 over all the period, 1 over all the period. Integral from 0, this is 0, to this point. This point is T on, because this time is from 0 to T on, to T on. The amplitude value is VD. V sub D, dt. And then the integral on. We can write the formula in another form. This is square. This is square, right? This is square. What's the area of the square?
Base, that's right.
Okay. The area of the square, height by width,
Yeah.
height VD with T on. That's it. VD. Or from this one we can say 1 over TS. This VD here T from 0 to T on. Or equal VD over TS, T on minus, instead replace it T on minus 0,
Yeah.
minus 0, okay? So now, 0, 0. So now VD, T on divided by TS, duty cycle, right? We say VD to define the duty cycle. This one, 2, 3, page 4, this page 4. Okay, duty cycle T on divided by TS. So T on divided by TS. Duty cycle, so VDC equal duty cycle time VDC. This is output this is this input voltage. Output voltage, input voltage. Now, duty cycle range between 0 to 1. Why between 0? Duty cycle, we define the duty cycle as T on to Ts, or T on to T on plus Ts. If T on 0, 0 divided by T of duty cycle, 0. If T of 0,
B will be 1.
T on to T on duty cycle. So the duty cycle from 0 to 1. This is the range of the duty cycle, but maybe 0.5, 0.4, 0.6, okay, 0.5. If the input voltage 100 volt and duty cycle 0.5, V out will be 50. So V out less than V input. So this is step down converter. So V DC less than or equal VD. So I mean this is step down converter. Any problem on this point? Any problem? VDC less than or equal V input. VDC less than V input. I will give you example like this one, but do you have any question about this?
The shape is always square, right? I mean, it's always
Yeah,
constant. Yeah.
square. Yes. Square. Okay, square. But what does mean by DC, VDC? See, VDC or V average or V out is the distribution of this square to one period. So the DC will be here. This is VDC. Okay? This value of good question. This is DC. Okay? But the output is square. Okay. But I need this DC voltage. Average. The average means the distribution of this area in TS. One period. Okay? Because this area here, okay, on, but here 0. So the average of this area for all the period. Okay,
Yes.
during TS, not just T on. Okay, but if we calculate V out RMS, no, the V RMS does this period, no DC, because the output signal consists of two components, DC component and AC. DC component, this is DC component. AC, no, it's AC, still AC, same period, same this one. You're T on. This is DC output, but it includes DC and AC components.
So VRMS only for AC.
AC, RMS, AC.
Okay.
DC, DC. Okay? So now, this one, let me just study this example. If VD equal 100 volts, duty cycle 0.6, then VD VDC equal DVD 0.6 times 100 equal 60 volts. Here VDC less than VD means this is step down converter. This is step down converter. VD the input 100 volt, VDC DVD V given, so VDC equal DVD, so the output voltage 60, because this is input, this is input. And this is output. Any question?
But the formula is the same with VRMS, right? The integral
No,
formula.
for RMS, I will write it. Okay, difference for
Good.
RMS.
So VDS is greater than VD, can be step up.
Step up. Step up. Difference, yeah. Difference concept. Now, V output mean square. V output means square. Root is root. Mean 1/TS. Integral from 0 to T on square. So VD, let's see now, VD square dt. And because this
Will be the same.
it's maybe square or rectangular waveform, so we can direct the amplitude square by the width. Direct. Okay, no need to take a VD square divided by TS, T on. Now T on to TS duty cycle. So we have RMS equal VD. Sorry, this is input voltage. Okay, and this is output voltage, but not DC. And this is a duty cycle. Out RMS.
Yeah, we don't have it in our diagram. In the diagram?
The diagram,
Yeah.
diagram just VD, V out, okay, is not voltage level. This is just the VDC, the DC voltage level, but this is AC.
Yes.
No, yes. And again, now we have V out DC is V out DC equal duty cycle VD, and V out RMS as AC equal square root D VD, and I out DC equal V out DC over R, or equal dVd over R, and I out RMS equal V out RMS over R, or equal square root dVd required for this one. And,
And the graph, it will be the same, right? It will be the same square, right? For VORMS. It like the picture, it will be similar, right?
I answer now this question. No way for RMS.
Yeah.
DC, this is DC. RMS is, this is just
Same thing.
term and AC. This is term and AC. That's no need to write. Also the DC just to indicate the RMS, but the DC, but the RMS is no area. It's not area. Why? Because VD square. This is not area, but VD by time is area. Area under the curve. But VD square times T on, no, this is not area. Not area. This is AC. But now, I have another point. This one. Okay, we say V out DC equal dVD. I have another formula for the output. Okay, according to Ohm's law, I equal V divided by R. Okay, but in terms of a duty cycle, dVd over R. Okay? But I want I out DC in terms of ID. See? Again, let me draw the circuit, this base, this input voltage VD, and this is R. VDC, this is IDC, and this is ID. Okay? This collector, emitter, base. We say V out DC equal dVd, right? Now I out DC equal 1 over dID. 1 over. Okay? V out DC equals dVd, while I out DC equal 1 over dID. Okay? This equation is very important. Why we need ID? We need ID. Why we need ID? Because ID is the output of the solar cell panel. Okay, I will explain, just write this one, and I will explain how to use the DC to DC converter with the solar panel. Okay, with the solar panel. Number 4, right? We have 5 and 5, 6. We have 2 weeks more. Week number 7, exam 1, and week number 8, midterm exam. Okay, almost. Because now 4. Maybe next semester I will suggest 4 classes to the department for graduate students. High voltage DC, machine fundamental drive. Fundamental drive machine, advanced drive machine, and power system stable. So I want to know few yes, which class you need?
I think we do this process.
High DC voltage is good
High
too.
DC voltage, yeah.
We took we took
Yeah.
Okay, so two classes.
yeah.
Yes, I will teach two of them, two classes.
High DC
Yeah.
And
and
Victor
machine, and
Coffee,
machine,
another.
I take advanced,
So,
or you could take it fundamental.
So depend, I will suggest to the department and
Wow, so mình hên quá
I
vậy.
will discuss
Mm.
your, I discuss with your, I will discuss with your Omar about that.
Đâu có thái gì đâu mà.
Because
Or like
these classes not offered last year and this year, so we will offer next semester, next year. Okay? So maybe most students need advanced and fundamental of electrical machine drive.
fundamental.
Cái đó anh chưa lấy đúng không? Cái HVDC với lại cái fundamental là hai lớp đó.
Fundamental and advanced, yeah, two classes.
Yes.
No, it's the same. I don't know.
Stability?
The advanced I suggested with Dr. Ali, but I don't know.
Check those two first. He teaches the next
No.
semester after. Because those two,
So that
he's a chance to take it. If he doesn't teach,
No.
you don't get a chance
I
to take those
suggested
classes.
to Dr.
This is what
Ali
he obviously gonna teach,
to
but not next
suggest
semester.
this
Just leave it at the
in
end.
class. Okay.
Okay.
But
Just
the
take it with him.
syllabus is different.
Take with him.
The syllabus should be include the generalized machine theory, matrix, information of the machine, not the same, but last year, no, they put it the advanced and fundamental same in the syllabus.
you have to change that.
Fundamental, yeah, sure, I will change it. Or if Dr. Kofi teach it, he will change it. The syllabus, sure. Okay? So this is for spring. For summer, maybe I will offer renewable energy. No, renewable energy, sorry. Wind and solar cell
This is a
generate.
we didn't take it.
No, this is new.
It has to be on the
It's
same.
a special topic and solar cell and wind turbine sources. Not
You could take it
renewable.
fundamental.
It's different.
So we cannot do it in the spring.
Yeah, I take it advanced.
No, no.
Yeah,
High
you want-
DC and fundamental.
Yeah,
Machine drive.
because
Good. Fundamental machine drive.
it's summer.
Yeah.
It's summer, I need this in summer, why? Because we need more students.
You're gonna take it. Yeah.
Thành và sao không có sao
And
nữa
this
và
is
sao
new.
không có sao.
Yeah, big mistake. Yeah. Those two classes good, Dr. Abu.
HVDC and
Yeah.
the fundamental machine,
Yeah, those two classes really good.
yeah, for the fall.
Next semester, no, spring.
Spring, yeah.
Yeah.
I
next
worked
semester.
it on.
And the fundamental
Of machine.
machine.
Oh.
drive,
HVDC
yeah.
and fundamental,
Oh.
yeah.
I worked it on fundamentals. Okay. And advanced and stability maybe Dr.
Coffee, yeah.
Or
Or
to take them go.
yes, maybe Dr. Coffee just advanced.
Okay, he teach advanced.
I will,
Don't have
follow.
stability. They have
Yes.
stability.
Okay. Now,
He's teaching stability.
this formula is very important. Why? Example.
Yeah, because right now, like, stability and fire electronics. Oh,
Design a solar cell system with the following. That. See? R load equal. See, I changed the letter. V out, V L, VDC, capital letter or small letter, uppercase, lowercase, same should be known the concept. This is V load DC. Okay? V load DC equal 200 volts DC load duty cycle equal 0.6 okay, that's it. This is design, right? Design should be first step, draw the circuit diagram. Okay? Should draw the circuit diagram. Circuit diagram? Okay. Design a solar cell system with the following data. RL, load using a duty cycle. Duty cycle, where is the duty cycle? Where you talk the duty cycle and DC to DC. I don't know, is now as just step down, so we will use step down, okay, and we have 200 volt output. I can put here step down converter, okay, but the exam, no, I will decide step down, step up, or I will give you some numbers and you should know this is step down or step up. You will use step down or step up, okay? But now it's because we took just the step down converter, this one. So now draw the circuit diagram, this one, RL equal 100 ohm, this is V load, transistor, you can use any switch device or transistor. This emitter, this collector, this base. See here, this is IL DC and this is ID. When this is not open circuit, this is connected to the control circuit, but is sometimes it's dirty, but it's connected to the circuit. This positive, negative, VD, and here source. First step, draw the circuit diagram, okay, and then we will design this one. You are designer now. First step, we draw the circuit, then should be calculate VD and ID. Calculate VD and ID. Then after that we will design the solar cell panel or panels. This example, there are two circuits. First circuit is a general circuit. One panel equivalent, but then we will calculate the multiple panels connected series or parallel or depend on the VD and ID, depend on VD and ID. So now, first step, the calculations is VDC, V load, DC equal duty cycle, V. V load DC, 200. Duty cycle, 0.6. V. So VD equal equal 333.33 volt. We need solar cell generate 3.33 volt. First of all, this large voltage, so should be cascade more panels, 3 or 4 or 5, depend on the available the market. Okay. Now, ID. Let me check ID also. I load DC equal V load DC divided by R. We have V load DC. We have V load DC. V load DC 200. Divide R 2 ampere. So 200 divided by 100, so equal 2 ampere. And now 2 ampere. I load DC equal 1 over D ID. We have I load DC 2 ampere. 1 over 0.6 ID. So ID equal 1.2 ampere. So now we need a solar cell generate just 1.2 ampere. 1.2 ampere, but the voltage is 333.333. 333 is difficult to get this voltage exactly same value, so you can make this one 360 or 340, more than the calculated value. So now choose 340 or 350.
Yes.
Choose VD 350 volt, ID 1.2 2 ampere. 2 ampere. You are a designer. You can, but please select VD and ID more than calculated value, not less than. Why? Because if you select ID less than 1.2 or VD less than 333.33, maybe the load need more power. Okay, so use VD and ID more than calculated value because you are designer. Now 350, we selected 350. We can use you can select 340 or 360. okay, but not 400, no, it's close to the value,
Okay.
calculated value. Now, 350, 2 ampere, okay, 350, 2 ampere, 350, if we have panel generate, we have solar cell panel generate 20 or 10 volt output at 2 ampere. So select solar cell panel of 10 volt 2 ampere DC right. So we have 2 ampere is 2 ampere, okay. 350 and each one 10, we can divide 350 divide by 10 equal 35. So here solar panel 1, 2, 35 generate 2 ampere, each of 2 ampere series, okay. This volt is 10 volt, 10 volt to 10 volt. Total voltage generated at the terminal of this grid is 350 volt connected to the DC to DC converter, connected to this one and this positive, negative, and this our load and the on. Okay, this collector, emitter, base. So we need 35. We need 35 solar cell panels to generate 350 volts, 2 ampere are connected in series. Yes, sir.
Why is it 10 volt per solar panel?
You are designer.
Yeah.
Okay, we select 10. Maybe another student select 20.
Oh, okay.
I will select 15 volt. Depend.
So
Okay,
does
you
it
can.
matter for that one or?
Yeah. This is, see, this is design. Design, you can select any value standard from the market.
Okay.
10 or 15, 20, 120. If you select 120, you need just 3 panels. 1, 2, 3. Okay?
Yeah.
3, 120, 120, 120
Mm-hmm.
equal 360. In the exam, I will give you the data for different numbers available in the market.
Okay.
So you can design according to the table given.
Okay.
Okay? Available value. Same protection, power system protection. Oh no.
No.
Select the
The
CT
Oh, okay.
ratio and okay.
Yeah.
Same selection of
Okay.
the circuit breaker size or available 10 to ampere.
Okay.
Okay.
Yeah.
But 120 volt and generate 2 ampere, this is not standard. But 10 volt and generates 2 ampere available.
Okay.
Okay? But I will give you I will give you table for different sizes available.
Okay.
Don't worry about that. Any question? Any question? I think it's ready 10 minutes. After the break, we will continue. Stay up. This is down tomorrow, right?
Yeah.
Yeah, if you want to use
Which okay?
the step down or the step down, why?
Does your case is already checked by?
The load is maybe
Okay.
resistive and inductive load.
Is the line for that still that long, right?
Now,
30.
So, like,
Now,
2-3 weeks?
if you need the equations,
No, no, you put 8 hours for me, so, I think I'm gonna review your report.
that's the third.
No, maybe.
I don't like, we don't like this one because the compound.
Okay.
The same one, it's tricky being a review.
Summary.
It's tricky being a review.
V out DC equal
Cause you get blamed for everything.
duty cycle VD. V out RMS square root D VD. I out DC 1 over D. ID. And I out RMS equal 1 over square root D I. Just these equations required, and duty cycle T on divided by TS or T on divided by T on plus T off, or frequency times T on. Right? So these equations require and we have a very important factor for the DC chopper: power out, power in, and efficiency. Power out, power in, and efficiency. Yes.
IODC, why it is 1 over D? Because it should be proportional with VODC, right? Because IODC, no.
I out DC
IODC, yeah.
equal 1 over D ID.
Yeah, but,
Why?
yeah,
Why? Because power input equal power out.
okay.
Power
Oh, yeah.
in, I will write
You
this
write, yeah.
one,
Maybe
this
this.
question now. Because I want to write the summary and then we will start to discuss the power.
Okay.
Power in, power out.
No.
Power in is VDID,
Yeah, I got it now.
power out,
Yeah.
okay. Okay, I will discuss it. So, any question about these questions? This question, you can use this question or this lecture note in the exam, okay? Now, power input, power output, and the efficiency of the DC chopper. The efficiency of the DC chopper is, or DC to DC, DC to DC converter or DC chopper, same, is about almost 200%. But if there is any voltage drop across the switch, across the thyristor or transistor, or maybe 1 volt, 2 volt, 3 volt, the efficiency dropped to 99 or 98, 97. Okay? So now, power calculations, DC support, power, calculations, and step down, step down, convert. Power input equal to the transistor connected to the input voltage VD and ID, and connected to the load V load, I load, okay. See, power input equal VDID, VDID. Power output equal V out RMS square divided by R. Efficiency percent equal power out to power times 100%. That's it. So this efficiency is to 100 or 99%. But the efficiency of the solar panel, is 25 or percent or 26 maximum. Okay, so power out, power in, power out as output power or input power here, input power out. Okay, maybe you will ask me about why here we used RMS, not DC. Yes.
We don't use the AC.
We used AC, not DC. Why? my question. Why we use AC, not DC? And the efficiency or the power outage. Why?
So
We use
here,
V out RMS.
RMS,
Why?
about the RMS is
AC, yes, AC, okay, AC. AC, but why we use AC voltage or RMS voltage, not DC? I can't use here V out DC to why we use RMS, not DC?
That's what helps calculate your efficiency, your RMS value.
RMS?
We're calculating the output power.
Yeah, because the efficiency depends on the RMS value. Okay, not on the DC. Okay, then with DC, that's okay. But efficiency depend on the RMS. Output depend on the RMS. Okay, or efficiency depend on the RMS. Okay, not on the DC. Okay. Now, therefore, we calculated or we tabulated V out RMS, the formula sheet or with the equations required. Okay. Now, how do you need this one?
This is still talking about DC, right? Not AC.
Sorry?
This is about DC still, right? DC converter.
Yes, this is DC to DC converter, but for output calculation, we
Yeah.
use RMS value, not DC.
Okay.
Okay? For output, see, we can say power out equal V out DC square divided by R. But no, we use V out RMS square divided by R.
Okay.
Okay? Last semester I told you about one example in one book, some books or maybe Lander or I don't remember which book is used the output voltage RMS in the rectifier. No, the rectifier should be DC. Okay. But here, this chapter, V out RMS. V out RMS, use V out RMS as output. Okay? Output power. Consider the voltage RMS, not DC.
doesn't the chapter, but if you
Yeah,
use
because it is chapter.
rectifier, you have to use it in DC.
Different
Okay.
concept. Okay. Now, we discuss now the load as resistive load. We say resistive load. Step down buck converter with resistive load. So now two, this is with resistive. Now step down or buck converter with resistive R, L, and we need Renewable diode. Renewable diode. This is diode. This is V, L, VD. This is ID. Okay, and this base, this collector, this emitter, and this is I load. This is I. Okay. Because this class is not power electronics, it's renewable energy sources class. No need to drive any form, just use the formula direct, okay? Because let the time for the solution and design, not for the drive VDC, VR, okay? No, no need to do any derivative, okay, and derivative for the equation. Just draw the circuit diagram, then write the formula direct. Okay, power in, power out, efficiency, VDC, VRMS, IDC, and direct is the formula. We have also two modes. One mode when the transistor is on or the switch is on, and second mode when the transistor is off. So now this one. Transistor on or switch on. VD, this is on, and this is V load, R, L, and the current follow this one, okay? Here, switch, off. VD, R, L, see this is the diode, will be short circuit. Why? Because first time the inductor will charge the current, and the second time when the switch is off, the inductor discharge the current. See the direction? Discharge the current in the diode. So the diode will be on. While here, because the current will follow this this direction, no current follow from the negative to positive terminal. The diode should be current just this direction. No current follow in this direction. So the current will be follow will be
Because the line goes one direction.
yes.
It doesn't go the that
Yeah.
reverse.
The current flow forward.
Forward.
Okay. No current reverse. Okay. Okay. No current in reverse direction. Should be in this direction. The current flow is very important to operate the diode or no. So an operation of the diode. Current flow here and current flow this side. Okay, this diode off and here the diode on. Diode D on. Here D off. Diode off. Okay, this is the mode of the operation.
This is for this die, no?
For this,
Not the other die.
What?
That would be original die.
no, Zinardal is different. Zinardal should be, should be work in the reverse bias, okay? And reverse should be, okay, the direction. And Zinardal using in stabilizer circuit. Okay, so no need to add Zinardal.
Oh, we cannot do it.
Yeah. So now here the diode is on, and here the diode is on. Okay. Diode. Off. Switch. On. Here diode on. Switch. Off. Okay. Any question? Okay, is enough for today or you want more? Is enough for today. Next week we will continue this time, okay? With this concept, and I will give you equations for the voltage, current, and dimension of the output current, because this current will be charge, discharge, charge,